Yes, we're recording now.
Okay, cool. Okay, so it is my pleasure to introduce Asgar Jamneshan from UCLA, and he's going to talk about some aspects of uncountable ergodic theory.
All right. So first, thank you very much for inviting me to this webinar. I'm going to present some work which is drawn from a couple of papers, mostly with tau, but I will also talk about a forthcoming paper with Polona, Rachel Greenfield, Anina Iseli, and Jose Madrid. So I'll start by giving an introduction into abstract probability spaces. So let's start with Boolean algebras. So Boolean algebra is a structure which is given by a set and two binary operations and a unary operation and two distinguished elements 0 and 1, which satisfies the Boolean laws. So basically the first property tells that both the binary operations are associative. The second one tells that they are commutative. Then the third one tells that the two binary operations, say, distribute. And the fourth one is called the absorption laws. And basically the last, this one is a negation rule. And here the last one are idempotent rules. So probably you'll all have seen them. And we can define on any Boolean algebra also an ordering by just declaring A to be smaller than B whenever the intersection or the meet of A, B is equal to A. All right, so let's see some examples of Boolean algebras. So a very simple example is just a finite field on two elements, which is also called the trivial Boolean algebra, which is just consists of two elements, 0 and 1. And if you consider it as if you see it as a finite field, then the intersection corresponds here to multiplication. The join operation corresponds to addition, and the negation just is taken minus of either 0 and 1. And this simple Boolean algebra is, of course, complete. So what I mean by complete is one calls a Boolean algebra complete if one can form the join and the meet of any family inside the Boolean algebra. So let's see another example of a complete Boolean algebra. So we take just any set and then we consider its power set. And then this is now a very familiar object. So we consider the power set together with the intersection union complement, and then 0 is here the empty set and 1 is here the whole set. And clearly any power set is complete. So the intersection of any family of subsets and the union of any family of subsets is again a subset. So let's see another example, which will be useful a bit later in the talk. So suppose X is a topological space and take all subsets of X which are closed and open at the same time. And now, again, consider the usual set operations on this collection of subsets. Then this is a Boolean algebra, so it satisfies the Boolean laws of the last slide. But this Boolean algebra is in general not even sigma complete. So by sigma complete, I mean that countable joins and countable meets exist. So to see an example, consider as a topological space the space consisting of 0 and 1 over n for all positive integers. and consider on it the topology, which it inherits from the real line, then it is not difficult to see that 1 over n, each singleton 1 over n is closed and open, but their union, which is this collection here, is not closed. Okay, so the example which will be most important for us is what is called the measure algebra of a measure space, and here we focus on probability spaces. So suppose you are given a probability space and now form the set n mu, which is just all null sets which are already included in the sigma algebra A. So that's an ideal in the Boolean algebra. That just means that any subset of a null set is a null set, and the union of countably many null sets is null. And what we can do, we can quotient the sigma algebra by this ideal. And the way it works is that we identify two elements in A whenever their symmetric difference is a null set. Now, this is now a quotient structure, and the Boolean operations of intersection, union, and complement can be defined also in this quotient structure in the natural way. So we define just the intersection or the meet of two equivalence classes of measurable sets to be the equivalence class of their intersection, and similarly also for the union and the complement. Now, a surprising fact about this measure algebra is that it is complete. That means that in the measure algebra, we can form the union and the intersection of arbitrary family of equivalence classes of measurable sets. So in particular, uncountable ones, which is at first a bit counterintuitive because a sigma algebra of measurable sets is usually only closed for countable unions and intersection. Let's see a short proof of that fact. So suppose we have arbitrary family of measurable sets, so equivalence classes of measurable sets in this quotient algebra. And what we can do, we can form the supremum over the measure of any countable subfamily, of the union of any countable subfamily of that family. So that supremum is just a supremum of real numbers. So in particular, there exists a countable sequence which approximates the supremum from below. And this countable sequence corresponds to families, so countable subfamilies of this family EI. So let's choose such a sequence. Okay, so we choose a sequence of countable subfamilies such that the union of their measure approximates C from below. So now if we take the union of all those countable families, this is still countable. And the measure of that union must be C. So otherwise, by contradiction, one can find one more element which one can add to that family. And so now we can just set E to be the union of this countable families. And one can see that in that Boolean algebra, that union here is a supremum or the join of that family. Okay, so that means that any element EI is different from this E up to a null set. So there is a consequence of this result, and that is that the space L0 of that probability space, so of equivalence classes of real valued measurable function, is Dedekind complete with respect to the almost sure order. So that means that any bounded set in the almost sure order of measurable functions has a supremum and an infimum. So that set can be, of course, also be uncountable. There is also another nice correspondence between the measure algebra and generally LP spaces, is that any equivalence class in the measure algebra corresponds to the equivalence class of the indicator function in any LP space. So in some sense, it is natural to work with the associated measure algebra instead of the probability space itself. And it is also superior to the original probability space as it is complete. So we can also perform uncountable operations. And another advantage of the measure algebra is that we don't have to worry about null sets anymore because we have thrown them out right from the start. But there is a caveat to that. And the problem is that once we quotient out the ideal of null sets from the probability space, then we have no points anymore in the quotient algebra. In particular, we have no underlying set if you want to work directly with the measure algebra. And unfortunately, this can also not be repaired. So there is an example which goes back to Loomis and Sikorsky, which show that already the Lebesgue probability space, if we quotient out from the Lebesgue probability space the ideal of null sets, then we cannot represent the measure algebra by a concrete algebra of sets. So represent here means that we cannot find a Boolean isomorphism to like a set with an ordinary algebra of sigma algebra of sets, which is isomorphic to that quotient algebra. So that means that we have to somehow find a way to work on the measure algebra or do measure theory on measure algebras without having access to points. So this already causes very basic problems. For example, how to define a measurable function if you don't have a set of points. So one way to do that is, instead of working with measurable functions, to work with Boolean homomorphisms. So for instance, start with a classical function, measurable function, f from x to the reals. And then you can consider the pullback map. So the pullback map maps any element of, let's say, the Borel sigma algebra of the reals to the sigma algebra by just taking its inverse image. And it is a elementary exercise to check that this map, this pullback map, is a Boolean homomorphism. It means that it respects the Boolean operations. And also it is sigma complete. So it respects countable unions and countable intersections. So this is just to give an example, but there is a whole theory that how one can do abstract measure theory, or how one can do measure theory on measure algebras. So point free in some sense, instead of concrete measure theory. And volume 3 of so Fremlin has a very extensive encyclopedic work on measure theory. And in volume 3, he develops quite systematically a lot of abstract measure theory. For instance, how one could define LP spaces, prove a Radon-Nikodym theorem, and so on and so forth. We will not need this machinery here. And we'll see later why. So now let's see how we can do dynamics on such measure algebras. So first of all, let's now forget about that X comes from a quotient of a probability space. Suppose X is just some sigma complete Boolean algebra. So that means that it is a Boolean algebra which is closed under countable unions or countable joins and countable meets. And we can just define, and by imitating the normal definition of a probability measure, we can just define a sigma additive functional on X, but having the stronger property that a set takes measure 0 if and only if it was the 0 element of the Boolean algebra. And of course, the whole set, or 1 in the Boolean algebra, will have measure 1. So such objects are also called probability algebras. And for probability algebras, we can also define what are measure-preserving maps. So these are just Boolean homomorphisms. So this is just a function which respects the Boolean laws when you map it to itself, and it preserves a measure for all elements of the probability algebra. And here we do not need to require that this Boolean homomorphism is sigma complete, because one can show that because of this measure preservance property, it respects automatically countable joints, and it's also injective. So that allows us to define an automorphism group of such sigma complete or on such probability algebra by taking all Boolean homomorphisms, which are and measure preserving Boolean homomorphisms, which are also surjective. So similarly, we can define the group of automorphisms of a concrete probability space. So this is just like all measurable isomorphisms, such that the inverse is also measurable. And both the transformation and its inverse preserves a measure. Okay, so that's also a group. That's a concrete group acting on points of X. And this one, we can think of this automorphism group as an abstract group of measure preserving transformations. So now we can introduce dynamics, both in an abstract and in a concrete way, by fixing a group gamma and considering a group homomorphism from that fixed group into that automorphism group. And then we will call, if we are working with a measure algebra, we will call such an action, we will call an abstract measure preserving dynamical system. And well, if we work with a concrete probability space, and we call it like a pointwise or concrete measure preserving dynamical system. So now there is a relation between concrete and abstract dynamical systems. So clearly, if we start with any concrete system, then we can obtain an abstract system by just deleting the null sets. So so we have here a group of measure preserving transformations of a concrete probability space, and then we pass to the measure algebra of that probability space. And since each T preserves a measure, its pullback defines measure preserving isomorphisms of that measure algebra. So the question is if we can reverse that process. In particular, that is important in order to have access to measure theoretic tools. So is there a way to like associate to any abstract dynamical system a concrete one? And there are two ways to ask this question. So one way to ask it is that suppose we have started with a concrete probability space, and we will see soon an example where such a situation occurs. So suppose we have started with a concrete probability space, we have quotient out the null sets, and then we have defined an abstract system. And there are very natural examples which happen to be of this form. Then we can ask if there is a way to realize that action on the original probability space. So if there is a point dynamics, which is isomorphic to the abstract dynamics once we do this deletion process to the concrete representation. So the other question, so that's one way to ask this, the question of the reverse process. The other way to ask this question is that suppose we have given an abstract system and we do not know that this probability algebra is a measure algebra. So can we model this abstract system by a concrete model with the same property as before? And if such a model exists, or if many such models exist, is there a canonical choice among such models? And I will clarify soon what I mean by canonical. So let's start with the first question. So unfortunately, the first question cannot be always answered positively. So that only works under certain countability or separability and even continuity assumptions on the action. And there are two well-known answers to this. So one is a theorem of von Neumann, which tells that if the acting group is countable and discrete and the probability space is countably separated, which means that there is a countable set of measurable subsets of X, which can separate points, then any abstract action on the measure algebra can be realized as a point action. And then Maki has a slight generalization of that theorem, which where the group can be any locally compact Polish groups. And X must be a standard Borel space. So that means that basically that means that X is a Polish space, and the sigma algebra is a sigma algebra of Borel sets. And the action must be continuous. So here continuity, there is a way to formalize continuity because there is a metric on the measure algebra. So this metric is basically the restriction of the L1 metric, if you consider that embedding of the measure algebra into LP spaces. And if with respect to that metric, the action is continuous, then T can be realized as a concrete action, as a concrete system, even with a property that the action is jointly Borel measurable. Okay, but now let's see a counterexample, and this counterexample somehow is a very natural example. So this concerns a symmetry group of an infinite dimensional Gaussian measure. So suppose nu is a standard Gaussian measure on the reals, and consider the infinite dimensional Gaussian measure on R on this sequence space, which is just an independent product of this one-dimensional standard Gaussian distributions. And what we can do is that the small L2 space can here be identified with some closed subspace H, which is also sometimes called the Cameron-Martin space of that Gaussian measure inside L2 by taking any sequence and associating to it this sum. So so now the orthogonal group of that small L2 space acts on H, and the action is given as follows. So first take a orthogonal transformation of L2 and then apply it to the sequence. And then if we have the associated element in L2, then map this element to that shift here, or to that sum where those coefficients here result from the from the transformation of that sequence here. So now in 2005, Glasner, Cyrilsen, and Weiss proved that so this action is only defined almost surely. The action of this orthogonal group on that probability space. So it is not a pointwise action. In fact, it is an action of the associated measure algebra, and it's called the symmetry group of the Gaussian measure. So this action cannot be realized as a point action. And actually, this fails quite dramatically in the sense that any pointwise action of that probability space here must be trivial. They had actually provided a whole class of such examples, which are called Levy groups. So these are Polish groups which permit some form of measure concentration phenomenon. And later, their result was also extended in a different direction by Moore and Solecki, where they showed that like this group of continuous functions from a Cantor set to the circle group has a similar property. So any abstract action on its measure on a measure algebra cannot be realized as a point action. Okay, so so this raises the question that if we want to work with such a dynamical system, so how to do basic measure theory? So one way to do that is to pass from an abstract system to a canonical model. So maybe I should say right away that such a canonical model is not the original probability space, but it will be a different space which can model this action. So let's start with a probability algebra. And then what we can do, we can form the stone space of that probability algebra, which are basically all the Boolean homomorphisms from the Boolean algebra into the trivial Boolean algebra, F2. And yeah, this is like similar to like other duality phenomenons, like in harmonic analysis, where one looks at the character group, or so here in the context of Boolean algebras, the characters basically are those Boolean homomorphisms into the trivial Boolean algebra. And that's a stone space of a probability algebra. And this stone space is like some form of a generalized Cantor space. So it's a compact Hausdorff space, which is totally disconnected. And on this stone space, we can consider the bare sigma algebra. So the bare sigma algebra is a sigma algebra which is induced by all continuous functions on the topological space. And there is also the ideal of bare meager sets. And what one can show, and that's so first of all, one can show that the simple stone duality would say that this underlying sigma Boolean algebra is isomorphic to all Kloppen subsets of the stone space, but this isomorphisms only respects finite joints and unions. In order to have also a sigma complete Boolean isomorphisms, one has to quotient out those meager sets. Anyway, that's a bit technical. But there is a way to associate with this probability algebra a concrete space. And we can also then define a measure on that space by just using this isomorphism here. So we define the measure on any bare set on that stone space to be the measure of its image inside the probability algebra. And this probability space, one can show that this probability space, so the null sets of this probability space are exactly the meager sets. And this probability space, if we quotient out from this probability space the null sets, then it will it is isomorphic to the original space. So we call this stone space, sometimes also called stone model, the canonical model. And it has been used already in dynamics before. So there is a very nice paper of Ellis where he uses this to relate some ergodic theory to topological dynamics, Fremlin uses the stone model very frequently in his book in order to develop measure theory for measure algebras. And there is also this book by Eisner, Farkas, Hase, and Nagel, where they actually take exactly that perspective to dynamics. And also a recent paper of myself with Tao, where we use this to develop some abstract or uncountable measure preserving dynamics. So what is nice about this model is that it has functoriality properties. So that means that if you have a probability algebra homomorphism, then there is a continuous function from the corresponding stone spaces. Well, it's contravariant here, the functor, which is defined like this. So you take let's say, a Boolean character, and then you just take the composition of that Boolean character with that homomorphism, and then you get a Boolean character on that space. So that's and one can show that this function here from the stone spaces is continuous, and it's also measure preserving, and the relation of passing from probability algebras to stone spaces and from probability algebra morphisms to continuous functions is functorial. So that's good, because it allows us to represent any abstract action in a canonical way. So we can, to any abstract action, we can associate a concrete action on its stone space. And now all elements of this automorphisms group will be actually homeomorphisms of the stone space. So they are not only measurable and measure preserving and point maps, but they have even the stronger property of being all also homeomorphisms. So what are some properties of this concrete model? So one a bit surprising but also nice property is that this concrete models is what we call satisfies the strong Rosen property. So the L infinity space over the stone space is equivalent. So to any equivalence class of bounded measurable functions, there corresponds exactly one continuous function on the stone space, and this equivalence is actually an equivalence of C star algebras. So, and the good thing about the canonical model is that now we can access tools from point set measure theory and probability. Like we can now, for instance, use Ries's representation theorem, because a stone space is compact. So we can use Fubini's theorem, we can use the Klein-Millman theorem, all kind of dualities in functional analysis. Another nice property about this canonical model is that it allows us also to construct products. So if you would like to, so suppose you start with two abstract probability algebras and you would like to construct the product measure, it is a priori not clear how to do that in a point-free way. But what we could do is that we could pass to the stone models. We could then form the classical product measure, and then we can quotient out, and one can show that this procedure satisfies some universality property of products. And it is also possible to form relatively independent products. So these are products where one has a common subsigma algebra and forms a product of two measures such that it is independent over that common subsigma algebra or factor. A very nice and useful property of that stone model is that it allows for what we call a canonical disintegration. So in in concrete probability theory, so if we, for instance, have a conditional expectation, so you have a subsigma algebra and then you have a conditional expectation, then typically this conditional expectation can be represented as a Markov kernel, or we can disintegrate, only if the underlying probability spaces are standard Borel. But it turns out, because of the strong continuity properties of the Stone model, that although those Stone spaces are typically very large, I mean, you can see them somehow as Stone check compactification, or they are somehow similar to Stone check compactifications in topology. So they are typically very large and very inseparable, but still it is possible to do to form some disintegration by using continuity and applying the Ries representation theorem. So yeah, I mentioned this. Okay, so this is a caveat. So those Stone models are typically very large and they're almost always inseparable. Let me also say that the use of compact models in ergodic theory is actually quite frequent, even in the standard Borel case. So even in separable and countable settings, as can be seen, for instance, in the classical books by Glasner, Furstenberg, and also the book which I mentioned earlier. And one of the reasons, for instance, one would like to have compact models or have for dynamical system, which are also sometimes called Cantor models, is that one can construct invariant measures by using, for instance, the Ries representation theorem. So okay, so one can see this canonical models as somehow this extension of this Cantor models, which are already frequently used to contexts which are not standard Borel groups, which are not second countable. All right, so let's see an application of this. So this is an application. So this is joint work with Durcik, Greenfeld, Iseli, and Madrid. And it should be, so we don't have a preprint yet, but it should be out very soon. So this is a classical theorem of Furstenberg, where we have an action of the integers on the automorphism group of some, let's say, standard Borel space. So, and these actions are commuting. So this means that the composition Tn with Sn is the same as Sn Tn. And then for any set of positive measure, one can show that this type of multiple recurrence averages, so that this limit exists and that this limit is positive whenever the measure of that set is positive. And in fact, one can say a little bit more. Actually, the times at which this multiple recurrence event happens, there are a lot of such times. This set of return times is synthetic. So what that means is that finitely many, so that there are only bounded gaps between those times, or that the union of finitely many shifts of that space already covers the whole integers. So this is a classical ergodic Ross theorem, and by Furstenberg correspondence principle, what one can also deduce from this ergodic Ross theorem, the Ross theorem about the integers, that that any dense subset of the integers admits three-term arithmetic progressions. Okay, so we wanted to generalize this result, where we now take, instead of a probability space, we take a probability algebra. And I will show our result for Z, but in fact, our result holds in more generality. I will comment on that maybe a bit later. So we have, again, two commuting actions, but now on this probability algebra, which are, and then we have a very similar statement. The only difference is we replace those intersections with these joins here. And so, yeah, I'll comment on the proof of that theorem also a little bit later, but we use this theorem actually to derive a uniformity statement, which I want to motivate now. So we can define for a subset of integers, we can define the lower Banach density of that subset to be this lim inf, where here the absolute or these bars here refer to cardinality. And these phi's here are bounded intervals in the integers. So now one can show that a set is synthetic inside the integers if and only if this lower Banach density is positive. So this let's say encoding of syntheticity will be important because we can then formulate a uniformity statement. So let me first read out what is here and then explain a bit. So we fix an epsilon, and then we will have some delta and eta, both only depending on epsilon, such that the following holds. So here the set of return times for this Ross type averages such that this Ross type averages happen with probability at least eta. Okay. So this set should have lower Banach density at least delta. So in particular, this set is synthetic because delta is strictly positive. But now this should happen for all sets in some probability algebra with measure at least epsilon. And now this should happen uniformly for all systems. That means like for all probability algebras, which are equipped with two commuting actions. So in fact, the statement here tells us that whenever we fix an epsilon and when we focus on sets, so only the measure of that set matters. So regardless of the system, we obtain some syntheticity result uniformly over all systems. So of course, the set of all, so the collection of all systems is not even a set, it is a class. So the question is how to prove such a statement. So I'll come to that later. So as I said before, so we can in fact, so I just for purposes of this talk, I focused on the integers, but in fact our this theorem, the abstract ergodic Ross theorem, holds for any discrete amenable group, and this group doesn't have to be necessarily countable. And this extent a result of Bergelson, McCucheong, and Zhang from the 90s. Also in the uniformity statement here, we can pass to a uniformly amenable discrete groups. These are just so we can not only work with one group, but with a whole set of groups where somehow the Föllner property in that groups hold in a uniform sense. Let's comment. So first, if you want to prove this abstract ergodic theorem, so let's comment what are the differences to the classical theorem of Furstenberg. So the classical, so Furstenberg's theorem, the way it works is that one reduces to the Kronecker factor. So the Kronecker factor is the largest group rotation, abelian group rotation inside the system. And then from proving that, and one can show that this Kronecker factor is characteristic. That means that by projecting on that factor, so it is enough to consider the convergence by projecting on that factor. And then to prove the theorem on that factor, so if one has an abelian ergodic group rotation, then one can do some spectral theory and approximate it with finite dimensional objects. And then the proof from there is kind of is easy. Another way is to use harmonic analysis. And so, but the systems we started with are not necessarily ergodic, but in the context of Furstenberg's theorem, that's not so much of a problem, because for standard Borel spaces, one can do ergodic decompositions. And so without loss of generality, one could reduce to the case of an ergodic system. So unfortunately, in the uncountable setting, there is no ergodic decomposition available. So what we have to do, we have to work relative. So there were two actions, S and T. So we have to work with a relative to the invariant factor, which is induced by one of those actions, S. And instead of, and then we have to do basically the same analysis, which is done here, relative to that, over the fibers of that invariant factor. But to do that, we need to pass to a canonical system. And the characteristic factors for the convergence for the Ross type convergence theorem are the compact extensions of this invariant factor, both for the for T and the action as composed with T. And at this point, we need to apply some. So similarly to that above, we need to apply now a conditional spectral theory. So conditional spectral theory means that we have to kind of relative to that space, so over the fibers of that space, we need to do some spectral analysis. But the point here is that you want to do the spectral analysis over the fibers of a probability space. So one could imagine it maybe at first it's over the points of that probability space, but in a way which is measurable. So that can be done by using some conditional analysis. And then once one has this description, so this allows one to represent again in the characteristic factors as some form of a finitely dimensionally generated objects, which are now in this context submodules. And then one does a similar argument as here, just for fiber-wise, but then one can find like a positive measure set for which convergence holds. And this part of the argument is pretty similar to the original paper of Bergelson, Mercutian, and Zhang. So yeah. All right. So now let's go to this uniform syntheticity statement. And let's see how to prove that. And we will see that to prove such a uniformity statement, which by the way could be also stated for just classical systems, one needs to pass at least our proof. In our proof, we need to pass to some uncountable system. But let me first check how much time I have. Not quite. Oh, there is still a bit of. Okay, so so to prove that uniform syntheticity statement here, we proceed by contradiction. So what is a contraposition of the statement here? So it would be that there exists some epsilon such that we find a sequence of systems. And in each such system, we find a set of measure at least epsilon. such that the lower Banach density of the set of the Ross type return times, so larger than 1 over n, is smaller than 1 over n. Okay. So if this happens, then this would contradict our uniformity statement. Now, what we have to do a bit of non-standard analysis here. So we have to pass to what is called the loop system. So to do this, we have to fix an ultrafilter, but for the moment, forget about like what ultrafilters are. Just imagine this. Just imagine. So first, okay, take some canonical model of that space. And now form this product here and imagine this product to be just sequences where each element of that sequence is in such space Xn. But you identify two sequences, say if they are equal, but finitely many of their entries. Okay. So you can always imagine such a construction. And one can associate to, in this product system. So these are stone spaces. So stone spaces are compact Hausdorff. So we can take their bare sets. And then we associate to such a product set, which are like products of this measurable set. We construct a measure. And so this is a standard part of that limit. So these are real numbers. And now if we take this ultra limit, so you can think of this ultra limit to be some real number plus some quantity, small o of 1, so which is very small. And if the standard part is just gives you in this decomposition gives just a real number. Okay, so that's a real number which kind of expresses an ultra limit of the measure of these sets. And then we can use Kara-Theodori extension theorem to take those from those cylinder sets, to pass from those cylinder sets to a sigma algebra and get a real measure on that. So that system is called the loop system, which is constructed from those sequence of systems. And one can also then define on that ultra limit an action. Okay, so you define the action on such an equivalence class of sequences by like pointwise actions on the elements of the sequence and then taking the equivalence class. And similarly, you can do that for S. So now we have a system, and we can pass to so we can delete null sets from that system to obtain an abstract system. Now we can apply our uncountable Ross theorem, and the uncountable Ross theorem would tell us that the set of return times for that loop system must be synthetic. So then we have to work a little bit, basically by using some Hahn-Banach theorems for invariant means to relate the syntheticity in this loop system to syntheticity in its component systems. And then one can show that if we take, like we had this sets En, if one can then obtain a contradiction by considering the ultra limit of these sets En, because the sets En are constructed such that in fact, if you pass to the ultra limit, then the return times must be basically empty, the way it is constructed, but that cannot happen because of the uncountable Ross theorem. Anyway, so that's, so what else? So we have two other results with tau. So this is uncountable Moore-Schmidt and Makitsima, but they're very technical. So I don't want to comment too much on them. And I have also, that's also in preparation, some uncountable Furstenberg Zimmer structure theory. anyway, this is all embedded in a larger term, in a longer term program, all these results to obtain uncountable Horst-Krauss structure theory. So Horst-Krauss, they proved for this type of, for instance, Ross type averages, they prove that the L2 limit exists, but like for longer progressions, actually. So one potential application of this whole program, once it's done, is that one could recover the inverse theorem for the Gauss uniformity norms and additive combinatorics from it, which, for instance, was used to count the number of arithmetic progressions in primes, for instance. Anyway, so I'm also working, so I just reported about the Ross project. We are working on an semi-ready version of that Ross project for amenable groups by extending some machinery which was developed by Tim Austin. And this is a work in progress with one of my students. Anyway, so I think I'm done. Thanks.
Thank you. Are there any questions?
Asgar, in uniform syntheticity theorem,
yes.
Why 2 commuting maps, not 3?
Oh, good question. So in fact, so first of all, because we have at the moment only the ergodic Ross theorem. So in order to stay, so actually syntheticity holds for all type of progression. So you could have n commuting maps for one system. Syntheticity would hold. That's actually part of the project which I'm doing with my student. But to get the uniform syntheticity, that would probably work for arithmetic progressions of length 4, which would be 3 commuting actions. But for the case of 5, there are actually counterexamples already in the standard Borel case that such a uniformity statement cannot hold. This is due to a paper of I think who is this, Bergelson, I think Kra and maybe Horst or Franzikinakis, I'm not sure, but there is a paper from 2005, 2006, which produces a counterexample. So one cannot expect a uniform. Okay, let me say it like this: one cannot expect a uniform syntheticity statement for progressions larger than 5, but one could expect this for progressions of length 4. And one can expect syntheticity for all systems with finitely many commuting actions.
Okay, thank you.
Sure.
Thank you. Any further questions?
Is there any attempt to try to have this abstract, lifting the ergodic theory to the abstract algebra level from not Roth ergodic theory, but let's say some sort of sub-additive, taking advantage of sub-additivity, because you mentioned partial order and etc.
I'm afraid I'm not fully understanding your question. So, so you mean like that the algebra itself is not a Boolean algebra, but some weaker structure?
Right, taking advantage of some sort of partial.
Wow, that's a very, very good question. I haven't thought about it.
Because you are taking advantage of the measure preserving transformation, but instead of that, if you weaken the condition.
Right. In fact, that's a very good question. Thank you. I have never thought about like going beyond Boolean algebra. So, and I think the reason mainly is that we use a lot of tools on the way. And certain tools, like, in fact, we use also some logical tools for certain structural analysis, which I didn't mention which I didn't mention. I just mentioned it very like on the way, like the conditional analysis, where I said we do conditional spectral theory. And those tools, because they come from logic, basically from Boolean valued analysis. So those tools would definitely fail for structures which are not Boolean algebras.
I see.
But one could still ask the question: to what extent the other parts of ergodic theory could be extended? And I have never thought about this, but thank you. Yeah.
Thanks a lot.